Well, so a good day to you all. So, we continue with our discussions on liquid extraction, and this is the last lecture which we are going to have on liquid extractions. So, therefore, if you remember in the last class we had started the continuous operations, right, the extractor under a continuous operation. So, in the continuous operation the steps of design had been mentioned to you, and we had also completed, or rather we had already discussed the criteria for choosing the solvent and compiling the property data over the entire operating range that you would like to take. Operating range includes the feed composition and the raffinate composition to which you would have to go, and corresponding to that the concentration of the solute in the fresh solvent or the solvent which is being used to start with, and the final composition of the extract solution. So, this comprises the entire operating range of the over which the extractor has to operate for one particular operation. So, therefore, the criteria of selection of solvent, it is the same, it has been discussed in the very beginning of the extraction class in the first lecture on extraction. Once it is done, then you need to do a feasibility test and you have to collect equilibrium data from the laboratory. Now, this particular exercise is quite important, as we will see in one of the illustration problems that we will be discussing as I proceed further. Next, we are supposed to decide upon the contactor selection. That also I had also mentioned, and you will be remembering that when we will be opting for a mixer settler, for most of the cases, particularly when the throughput is high, we would like to go for a continuous operation. Among the continuous operation, we can select a packed bed, we can select a sieve tray tower, and suppose the number of theoretical stages are very high, or else the interfacial tension is say moderate to high, as we had already discussed, we would like to go for any type of an agitated contactor. Now, regarding the agitated contactor also, I had mentioned and had shown you there are different types of agitated contactors. I did not go into the details of all these things. We had just discussed simply the basic structure of a rotating disc contactor, but if in any case any of you are interested to know about the Schiebel contactor, the pulse tray contactor, or maybe the car reciprocating contactor, during the interaction time, if you contact us, if you put up your doubts in the forum, we would be clarifying the doubts accordingly. Well, after the contactor selection, then you have to decide on the dispersed phase and the continuous phase. This also in the last class we had discussed about it, that the main factors they are interfacial tension, relative viscosity, and the flow rates. And I had also mentioned that the higher flow rate is dispersed for the packed bed and the sieve tray, and the lower flow rate is dispersed for all other types of tray. I had also mentioned that normally, although for gas liquid and vapor liquid contacting, particularly for vapor liquid contacting in distillation, we often prefer the bubble cap tray, but in this case due to low throughput, low efficiency of the bubble cap tray, we do not go for the bubble cap tray in this particular case. Now, after this, the next thing which is very important is the pilot plant design to obtain the mass transfer data. For mixer settler, if you remember, I had derived the basic equation for the holding time. We found that the holding time, it was a function of mass transfer coefficient and interfacial area, and I had also mentioned that just because in this case there are a large number of uncertainties. Why? Because the extractor, it involves the complex phenomena of droplet breakage and droplet coalescence, which is itself not an extremely predicted phenomena. Other thing is there is axial mixing and the radial mixing. Then see, we cannot avoid any sort of impurities. Whenever there are any sort of impurities, it significantly affects the interfacial phenomena as well as the equipment performance. Quite naturally, due to all these things, there is a lack of reliable data on both mass transfer coefficient as well as interfacial area. As a result, the estimation of process parameters from the fundamental theory, that is from the basic mass transfer equations, the equations which you have learnt in your mass transfer class, that is extremely difficult. And so, naturally what we would like to do in order to obtain data on the mass transfer coefficient as well as on the interfacial area, generally we perform the tests in the pilot plant. Now, when we perform the tests in the pilot plant, it is important, two things are important that we should remember. First thing is we have selected the contactor earlier itself. So, therefore, the pilot plant tests have to be conducted in the same equipment type based on the process considerations of the actual production. If we plan that, well, for this particular case we would have to go for a packed tower contactor, the pilot plant data will also be collected in the packed tower data. And the other important thing is the selection of solvent. Frequently we find that we select a solvent and for the pilot plant test we operate or we perform these tests with a synthetic fluid which has the same properties as that of the actual solvent. This often results in unsatisfactory results. So, therefore, it is important for you to consider that the pilot plant tests, they are also performed with the actual liquids, and when we are performing pilot plant tests, we should be performing both the extraction as well as the solvent recovery over a wide range of operating conditions. See, repeatedly when we keep on telling that, so it is just to emphasize upon you how important the solvent recovery part is for the extraction process. We cannot think of the extraction process in isolation, which I have mentioned earlier as well. Both of them go hand in hand. So, even for generating data for the pilot plant, we just need data on the mass transfer coefficient and interfacial area, which has nothing to do with the solvent recovery. But then also it is advisable that the pilot plant tests are performed over the entire process, including both the extraction as well as the solvent recovery over a wide range of operating conditions. Now, once the pilot plant tests have been conducted, you have obtained the data. Next, you need to have some particular scale up laws by basis of which you are supposed to scale up the pilot plant data to the actual plant conditions. We assume that the mass transfer characteristics are same in the pilot plant as well as in the actual plant. Based on them, what are the things that we should be scaling up? Quite naturally, the throughput will be higher in the actual plant as compared to the pilot plant. So, therefore, accordingly the diameter and the HETP of the plant has to be decided, or in other words diameter and the column length. So, these two are the parameters which have to be decided based on the pilot plant data. And therefore, normally these are the two equations which are used, where K1, M1 they are decided based on the particular contactor that you are selecting. K1 and M1 naturally they refer to the capacity scale up factors, and these two they refer to the efficiency scale up factors. And one more thing, just you should be remembering that when we are going for agitated columns, then there is an additional parameter which should be considered, that is the frequency of agitation at the same power input. This is almost similar, if you remember when we were discussing scale up for mixer settlers, there also we had scaled up assuming the same power input. So, in this case also we assume this, and accordingly the frequency of agitation is decided here. This has got an additional advantage that it gives us one more parameter that we can vary in order to optimize the operation. In this particular table, if you see, just for the packed and sieve, because we are going to deal with these two, I have put down the typical dimensions of a pilot plant. These dimensions they have been decided based on experience which have been gathered in different industries which use extractors for different purposes. Now, here I have put down the typical dimensions and also the process factors and the column variables as well as the variables. So, all these things have been put up. There are identical plant column, there is pilot column dimensions which are available for agitated contactors as well. Since we will not be dealing much with agitated contactors, I have not included them in this particular table. So, therefore, the next thing that you have done, so pilot plant tower, we have already discussed the pilot plant tower design and also the design of the actual column using the scale up relationships. The two important things which are left now to be discussed are the calculation of the number of theoretical stages, right. And once we have decided that, then based on the efficiency, the plate efficiency that we have, based on that we can find out the column height h equals to, which will be equal to NTS into HETP for a packed column, or it is going to be H equals to NTS into tray spacing for a sieve tray column. So, accordingly we can find out the H, and the other thing which is left is the tower diameter from flooding considerations. Now, regarding tower diameter, let me mention that you have you are already aware how the tower diameter is decided for sieve tray and packed columns in the case of vapor liquid and gas liquid contacting. These they are based on the flooding considerations, or these are designed based on the maximum mass flux of the vapor under flooding conditions, or the volumetric flux of the vapor under flooding conditions. We will find that in this case it is slightly different. We will find what is different and why the difference has to be taken into account. So, in this class primarily we are going to discuss the calculation of the number of theoretical stages and the estimation of tower diameter from flooding considerations. These two we are going to decide. Now, regarding the number of theoretical stages, I would also like to remind you that when we had discussed gas liquid, vapor liquid contacting, what did we do? We had constructed the equilibrium curve, we had constructed the operating curve, and then we had after we had drawn the two curves, if you remember, in this particular way. After that we had this is the line. So, therefore, this was the, for the distillation, this was the curve, this was the Q curve, and accordingly we had drawn the steps between the operating curve lines as well as the equilibrium curve, and we had found out the number of stages. In case of absorption also, if you remember, so therefore, this was the equilibrium curve, this was the line in the case of absorption, this will be the line in case of stripping, and accordingly we had marked off steps and found out the number of stages. In this case also we can do this under very special circumstances. Generally the process is not so straightforward, and you must have guessed the reason for it. The primary reason is the miscibility of the feed solvent and the extraction solvent between each other, as a result of which for most of the cases we have to refer to ternary plots or rectangular plots. And so, naturally, just because of that, although the concept is the same, the concept, it is based on the basic overall mass balance and the component balance, the same equations we are going to use, but just because of this particular miscibility and just because we have to go for ternary plots, the situation becomes slightly difficult in this slightly different, I should say. It is not difficult, slightly different in this particular case. I will explain the logic behind the particular technique, that how we have developed it, and then I will be giving you a series of steps following which you can find out the number of theoretical stages. And remember, in your assessment what will be given, maybe the entire process you will be not be requiring, maybe we would be telling you to derive the, or rather to formulate the operating line equation, or to find the mixture point delta, etc. So, you will be given such type of piecemeal questions from the estimation of the number of theoretical stages, right. So, now with this particular background, let us go to find out the number of theoretical stages. So, therefore, mostly as I have mentioned that we have either a rectangular plot, for most of the cases we take a rectangular plot. What happens in this particular rectangular ternary plot? Whatever we have done it, we can do the same thing on a triangular plot as well. In a rectangular plot, what we have on the y axis, we plot the composition or the mole fraction of the solute in the raffinate, right, or the extract. So, in this particular case, we plot the mole fraction of solute. For my case, B is the solute, S is the solvent, A is the feed solvent, and on the x axis we plot the mole fraction of the solvent, right. Now, x's referred to the mole fractions in the raffinate phase, y's referred to the mole fraction in the extract phase. So, therefore, when I plot xb versus xs, it means I am plotting the mole fraction of the solute to the mole fraction of the solvent in the raffinate phase, and this is the curve that you generate from here, right. And similarly, when I plot yb as a function of ys, it means that I am plotting the mole fraction of the solute in the extract phase versus the mole fraction of the solvent in the extract phase to give me the extract curve. So, therefore, the mole fractions of the solute and the solvent in the raffinate phase are given in the raffinate curve. The mole fraction of the solute and the solvent in the extract phase produce the extract curve. Both the curves, they meet, this has already been discussed, they meet at the plate point, which marks the limit of immiscibility between the two liquids. So, therefore, this is the zone of immiscibility, you already know. Beyond the plate point, whatever is there, this entire region, in this region A, B and S, they are miscible in all proportions, as a result of which if you have to perform solvent extraction, then in that case you have to perform this, or rather you have to limit your operations within this particular immiscible dome. Now, in this particular immiscible dome, you can very well locate, say, the point F, right. Now, if suppose we do not have any amount of solvent in the feed, then maybe the feed composition will be located somewhere here. Okay, but suppose there is some amount of solvent in the feed, then naturally the point will not be located on the straight line connecting the feed solvent and the solute, or the straight line connecting A and B, it will be inside the triangle, right. Say maybe it will be somewhere here under that condition. Same thing, you need to locate the solvent point. If you are dealing with completely pure solvent, rather solvent completely free of solute and as well as A, which generally does not happen, because always we will be having some amount of recycled and recovered solvent, but it can happen when the feed solvent and the extraction solvent are completely immiscible. So, that whatever small amount of A is there in S, we can neglect it. Whatever small amount of B is there in S, we can neglect it. If we can neglect it, then we can assume that the solvent is 100% pure, or in other words, the solvent starts from, or rather the solvent point is this particular point. For most of the cases, the solvent point will be somewhere here, or if suppose it does not contain A, but it contains B, then in that case it can be somewhere here also, right. So, therefore, we can locate the solvent point as well. Now, if you remember that I had already mentioned last time when we were discussing regarding the ternary plots while discussing the equilibrium considerations, if you join, say, this particular point to S, then the mixture point is going to lie on the straight line joining F and S. More number of solvent, the mixture point keeps on shifting here, lesser amount of solvent, the mixture point is towards here. So, therefore, the mixture point is somewhere, it lies somewhere on the Fs line, and it depends upon the relative proportion of the feed solution and the solvent solution by the inverse lever rule, or in other words Fm divided by Ms. This gives you the amount of solvent and divided by the amount of feed, both of them taken in kg moles per hour or kg per hour, does not matter. So, therefore, the amount of solvent that decides the location of the point M. Now, finding the number of theoretical stages, it will be based on the graphical construction which we are going to discuss, and I will be discussing it in a rectangular ternary plot as I have told you, but the same thing is applicable for a triangular diagram as well. This I have already told you. What you need to remember is that all your compositions in the extraction solvent are denoted by Y's, and in the raffinate solvent they are denoted in the raffinate they are denoted by X's. This is what you need to remember in this particular case. So, now see, just like we had done for absorption and distillation, in this particular case also what we do, we perform this particular stage calculation based on the overall material balance and the component material balance. So, from the I have drawn the diagram here, this is F and it goes on this from the last stage, nth stage, Rn comes in, and from here S enters, which is nothing but the extract entering from the n plus 1th stage, and what comes out is E1. So, therefore, suppose I do the total material balance. What will I get from the total material balance? I will get F plus S. If you can see, F entering, S entering will be equal to Rn going out from here plus E1 going out from here. This is equal to M, isn't it? So, therefore, what does it mean? It means that suppose my F is here and suppose my En plus 1 is here. If I join, then M is going to be a point, and on that point will also mark the intersection between the final raffinate composition. Say the final raffinate composition is somewhere here, and suppose the E1 is here. Then if I join the two, then in that case M is going to mark the point of intersection between Fs and Rn E1, right. And so, therefore, what are the coordinates of M? To find out the coordinates of M, we can do the solute balance. From solute balance, we are going to get the y coordinate. From solvent balance, we are going to get the x coordinate, isn't it? So, from this should be from, not for. So, from solute balance or the balance of component B, we can locate M in what particular way? We can write it down as F Z B F, where B is our solute, plus S Y B will be equal to E1 Y B 1 plus Rn X B n, isn't it? So, and this is equal to M into Z B M. Actually, since we are doing the solute, this should be actually Y B M, right. So, from there we can find out Y B M or Z B M in whatever way you tell it. This is nothing but F Z B F plus S Y B divided by F plus S. If you are taking completely pure solvent, then in that case this disappears off. In the same way, from the solvent balance, if we take from the solvent balance, in the same way we can find out my X S M. This is also going to be the same thing. It will be FZSF plus SYS divided by F plus S, isn't it? And for most of the cases, suppose we do not have any solvent in the feed, then this disappears off and this gives us the x coordinate of the point. So, therefore, we know that M also lies on the E1 Rn line as well. Now, we can just rearrange the total material balance and the solvent material balance equation. Just how I rearrange it? Say F minus E1, if I write it down, this gives me equal to Rn minus S, and this I denote it as a difference point delta. What is this delta, you tell me? It is the difference of the net flow from any particular stage. This is the net flow out from the first stage, this is the net flow out from the last stage. So, from there similarly I can perform a solute balance also. If I perform a solute balance, just the same balance I can write it down in the same way, which is going to give me FZBF minus E1 YB1 will be equal to Rn XBN minus S YB, which will be equal to delta XB delta. In fact, it should be actually YB delta, not X, because we shall be getting the Y coordinate from here. So, from there what do we get? From here if you find, we are going to get YB delta, it will be equal to say F ZBF minus E1 YS1 divided by F minus E, and in the same way you can find out the XS delta as well. Now, we find that instead of doing for the entire plant, we can write down such equation for any particular individual stages. Say instead of writing it for the last stage n, we can write it for any particular intermediate stage. Say for example, this is the stage n, say for any particular stage we can write it down. When we write it down for any particular stage, we find that we get something like for any stage n, what do we find? R n minus 1 is entering plus S equals to E n plus R n, when we are writing right from stage n to the last stage, and this is equals to delta. So, from here also what do we get? We get R n minus S equals to R n minus 1 minus E n will be equal to R n minus S, which is nothing but equal to this. So, therefore, we find that whether we take up any particular stage, for any stage we find that the net flow out of this stage should cross through one particular point, which is the delta point, and this delta point therefore, it should comprise of all the, or it should be a point from where all the lines for which mark the net outflow from any particular stage should be located, isn't it? So, therefore, from here what do we get? We get that if suppose we have a point say FE1, suppose I join FE1 and I extend it this side, I join Rn minus S, or if it is En minus 1, and I extend it here, and I find that it joins at a point delta. So, therefore, it means that from delta, if I take a point which is connecting R2, say the raffinate which is going out of R2, and if I extend it, then it should this point should be E3, In the same way, if I extend it and I come to some particular point Rn and I extend it, then this should give me the point En. If I extend it, if it is Rn, then this should give me En plus 1, where n is any particular number of stages. So, therefore, there are two things on which the entire construction is based. It is based on locating the mixture point. Once you have located the mixture point, you know F, you know S, the R is usually specified, but in this case you have to remember generally this R prime after the solvent recovery is specified. So, therefore, since it is depleted of solvent, this R prime is going to lie on the y axis. So, therefore, how to find out Rn in this particular case? When you join the R prime with the S or the En plus 1, depending upon the concentration of the solute, then the point where this R prime meets this raffinate curve gives you Rn. So, once you have noted down Rn, then you know F, you know S, you know F, you know R prime, from where you know Rn by joining R prime and S. So, once you know this, so if the point M is known to you, then simply drawing a line from Rn to M2 to the extract curve gives you the E1 point. Moment you know the E1 point, what do you do? E1F you extend it backward and you extend SRN point backward, you get the point delta. Once this point delta is done, then what you do? From E1 you can draw a tie line. When you draw a tie line from E1, what do you get? You get R1 from because you know that this sorry, not E1, sorry, you know R1 because R1 and E1, these two are in equilibrium. For every particular stage we know that the exiting streams are in equilibrium. So, therefore, from here if you extend it you get R2, and moment you get from E1 you get R1, then from the delta point if you are joining, if you are extending it, you are going to get E2. From E2 you draw the tie line, you will get R2. From the delta point you extend to R2 and then extend it, you get E3. You can keep on continuing this particular feature, and the number of times you are doing this gives you the number of stages. You keep on continuing till you reach the point Rn here. This is the basic thing which you are supposed to do for the particular composition, or rather for constructing the number of stages here. The whole thing is already done to you very clearly. What we do, from R prime we have joined. I repeat once more, you have located Rn here. Once you have located Rn, the F point is here, the En plus 1 point, because we have not taken pure solvent in this case. So, therefore, you join this particular line, and then if you know M, then you join M to here, you get E1. You join F E1, you get and you join these two, you get the delta point. Then from E1 you have dropped a tie line, you get R1. From delta to R1 extended, you get E2. From E2 again you draw a tie line, you get R2. In this particular case we find R2 is less than Rn. So, therefore, we stop the construction here. So, this is the thing that you need to do. In fact, you can also geometrically you can find out x is delta, x b delta, just the way I have told you. So, therefore, once you have done this, so you know how to find out the number of stages. The only thing that is remaining now for you to think is how to construct the tie lines. This is the next thing which we will be doing in the next class. We will be discussing about this. Thank you so much.